So here is the question based on an atomic spectrum. The question is asked in a manner in a sim in a sample of a hydrogen atom, electrons are de-excited from the fourth excited state to the ground state. Which of these is or are correct? See, students, I have taken a questions in which more than one options are correct. But for the JEE mains, there will be always one option which is correct. Okay. So here I have taken this problem so make you understand the concept, and also I want to introduce that concept over here. So the question asked is this: which of the following statement is correct? Right? The question says is that I will draw the energy level. Let's say, sorry, S- this is n is equal to 1, which is also called as a ground state. This is n is equal to 2, first excited state. Then spacing I will keep equal. Usually the spacing, okay, let's decrease that also. Not an issue. Let's say if this is the energy level, first energy level, n is equal to 1, ground state. Then this is n is equal to 2, a first excited state. Then n is equal to 3, a second excited state, right? Then n is equal to 4, a third excited state, and the n is equal to 5, which is fourth excited state. Question asked is electron is getting de-excited from the fourth excited state to the ground state, right? Which of this is correct? Let's draw like for the first thing it is like electron is getting de-excited from the first state. I'll write here de-excitation of electron from first to final state, that is on this to the first, that is a ground state, right? This excitation is happening. Now, in this case, let us draw some lines which represent some series. So this is Lyman series, or I should say I should draw it in this manner. This is Lyman series. Please excuse me for the diagram. This is Lyman series. Then this is Balmer series. Then this is Lyman Balmer Paschen, and there is bracket series, right? So these are the different series which are observed over here. One, two, three, four, five. Fourth excited state to this. So no line is observed in a Fern series. This is what the first statement is. Like Fern series is Lyman. This is Lyman, Balmer, Paschen, bracket, and Fern series starts from here, right? So Fern series starts from here. N is equal to 6. Means from here the Fern series will start. But anyway, electron is jumping from n is equal to 5. So there is no line which is observed in a Fern series. This is true, right? Total 10 lines are observed in the spectrum. Like if it is this, then 4 lines of this, of the Lyman series, 3 lines of Balmer series, 2 lines of Paschen series, and 1 of bracket series, right? So this comes to 7, 8, 9, and 10. So this is also correct. 4 line in UV region and 3 line in 3 line in visible region. Like if we see that a Lyman series falls in a UV region, ultraviolet radiation, UV, right? This is UV region. Then Balmer is in visible. This is invisible. Then Paschen and bracket are in IR, 4 line in UV, and 3 line in visible, right? So 4 line, like this is a 4 line which are falling in UV. UV has a 4 line over here, and this is visible is having three, right? So this is also correct statement, right? One line is observed in a bracket. So this is Lyman, Balmer, Pasture, and this is bracket series. This is also true. So the option, all four options are correct for this. So this is about the atomic spectrum, how the de-excitation of the electron takes place. Okay, here is the next question. Again, this is a multiple option correct question. Keep that in mind that for the JEE main, there will be just one option correct. So here, question asked is if the wave number of the first line of a Balmer series of hydrogen atom is X, then here what they have said is a wave number of first line of Lyman series of a helium plus ion will be 108 times X by 5. Wave number of first line of Lyman series is series of helium plus ion will be 36 times x by 5 wavelength. Now then there is a wavelength, right? So we have a very good relation about the wave number. We know the number, wave number equation. This is wave number equation. Nu bar is equal to r z square upon 1 upon n1 square minus 1 upon n2 square. Like n1 square means what? If there is a energy levels this way, and let's say the electron is jumping from this to this, right? This is my, let's say this is n is equal to 1, this is n is equal to 3, and this is le- sorry, n is equal to 2, and this is n is equal to 3, right? So n1 is lower. N1 you can consider lower one on which it is getting de-excited, right? And N2 is the higher one. Right. See, it's very simple how to understand the bigger value and the smaller value. See, if N1 is the one which is this, if N1 is higher than N2, then what will happen? This overall answer will be negative, right? So N1 should be less than N2. So the question, coming to the question, if the wave number of the first line of a Balmer series of the hydrogen atom is X, now first series like of the Balmer, let's say this is N is equal to 1. This is how the energy level increases. So this is 1, this is 2, this is 3, and this is 4. Like Balmer series is from here. From here the Lyman series will start. This is the Balmer series, right? This is the Balmer series. This is Lyman series. Like all these lines will be a Lyman series. This is one of the first line of the Balmer series. Second line of the Balmer series is this. First line of Lyman series is this. Second line of Lyman series is this. Third line of Lyman series is this. Right? So first line of the Balmer series. This is what the first line of the Balmer series. So what is N1 over here is, so wave number will be is equal to R into Z is 1. 1 square will be 1. So 1 upon N1 square. So this is 2. N1 is 2. That is 2 raised to 2 is 4, and this is 3. 3 raised to 3 is 9. So this wave number will be is equal to r into 5 by 36. And what they have said that this wave number will be is equal to x. This wave number will be is equal to x. Therefore, what is r is equal to? R will be is equal to 36 by 5 into x. This is what my r is, right? So first option. Let's check first option. That wave number of the first line of Lyman series of the helium ion will be 108 times that of x. So wave number I will write for the r is Rydberg constant that will remain same. For the helium atom n is 2, sorry z is 2. So this will be z square will be is equal to 4, right? So 1 upon first line of the Lyman series. First line of the Lyman series means this is the Lyman series and this is the first line of the Lyman series. So n1 is 1, right? And n2 is 1 upon 4 because 1 upon 2 square it will be, right? So this will be r into 4 into 3 by 4. So wave number over here, wave number will be is equal to 1 minute, student. Think I made a mistake. It's not a mistake. Like my window is coming over here and you must be not be able to see that, right? So I'll do it again from here. What happened? So this is about R. Now option A, if I'm solving, then it will be wave number will be is equal to uh, R z square, right? For this z is 2, right? So I will write 2 square will be is equal to 4. 1 by 1 minus 1 by 2, right? For Lyman series, first line of the Lyman series. So this is what the first line. So 1 by 4. So this will be is equal to R, wave number will be is equal to R into 4 into 3 by 4. So R is equal to wave number is equal to 3 times R. So wave number, what is R is equal to? It is 36 by 5 x into 3. So this comes to 108, like this comes to 36 into 3 is 108 by 5 times x. So option A is correct. Since this is multiple, option is correct. You can try for the option B also in the same manner, wave number, and see if it is correct. Uh, it is incorrect. Option B is incorrect, right? Let's check for the wavelength. Let's check for the wavelength. Okay, let's solve option B also, not an issue. First line of the Lyman series of the wave number of first line of the Lyman series is helium plus ion will be. Like we have understood that first line wave number of the first line of the Lyman series of the helium is 108. So obviously option B will be incorrect. This is correct. Wavelength of the second line of the Lyman series. Now, what is wave number? Wave number is related. This is what the relationship between a wave number and the wavelength. So this I will write 1 by wavelength will be is equal to r z square 1 upon n1 square minus 1 upon n2 square. So I am solving for the C. So what was my r in that case? What r I was getting? I was getting r as a 36x by 5, right? This was the r which I was getting. So over here 1 by lambda will be is equal to r, and it is a wavelength of the second line of the Lyman series. Second line of the Lyman series means this is first line of the Lyman series. This is what the second line. This is 1, this is 2, and this is 3. The first, second line of the Lyman series. So this will be of the hydrogen atom. Means hydrogen means Z is equal to 1. 1 square will be is equal to 1. So 1 upon N1 is 1 minus 1 upon N2 is, this is second line of the Lyman series. So N2 is 9. So 1 by lambda will be is equal to R into 8 by 9, right? So lambda will be is equal to 9 by 8 into R. Now what is R is equal to? Sorry, not into R, into 1 by R. Like this lambda will go over here, will be 1 by R. So lambda will be is equal to 9 by 8 into 5 by 36 upon X. So this will be 9 4 za 32 by 5. So option C is also correct. What I am getting over here is lambda is equal to 5 by 32 times 1 by X. So since this option is correct, option D is incorrect, you know. So option A and C are correct for this too. So here is the next question based on the Lyman, Balmer, Paschen bracket series, that is spectrum. Okay. So here question asked is for any given series of the spectral line of the atomic hydrogen. Let delta V, sorry, it is delta wave number. A difference in the wave number is wave number max minus wave number minimum, right? Be the difference in the maximum and the minimum frequencies in per centimeter. The ratio of wave number Lyman, like difference in the wave number of the Lyman series, that is maximum minus minimum upon wave number of the Balmer series from the maximum to a minimum, right? So here there is a slide. This is delta nu bar. This is 27. So let's solve this question. That wave number is directly proportional to the energy difference. Like more is the energy difference, wave number will be directly proportional. So wave number formula is given as since this is hydrogen atom, Z will be is equal to 1. So formula I will write it to be 1 upon n r into 1 upon n1 square upon 1 upon n2 square. So for Lyman series, like Lyman is this 1, 2, this is what the Lyman is, right? So what is the n1 possible here for Lyman series? Max, wave number max possible will be from some de-excitation from the infinity to 1. So this is n is equal to 1, this is n is equal to 2, this is n is equal to 3, and there is say there is one line which is from the jump from the infinity to 1. That will be a maximum value. This is n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7, that way. So n from infinity to this, like large energy difference. So high wave number, right? So for I will write a new bar for Riemann series, a maximum new bar max will be what? It will be R into r into 1 upon 1 minus 1 upon infinity square. Again, it is infinity only. So this r value, what we can take is energy difference is 13.6. We are taking it to be 13.6, right? So this will be is equal to 13.6 upon 1 minus 1 by infinity. This is new bar max. That is wave number. Minimum will be 13.6, 1 by 1 minus 1 by minimum is this, no? Energy difference. So this is going to come to be 1 by 4. So this will be a difference, we need to find a difference to be is equal to like difference between this. Like 1 by infinity, I can just consider that to be just 16.3, and this I can consider to be is equal to 13.6 into 3 by 4, right? So it is if you want to find a delta bar, a difference will be 13.6 minus 13.6 into 3 by 4. So this is 13.6 into 1 minus 3 by 4, right? So this comes to 1 by 4. So 13 by 6, 4, right? So this comes to 13.6 by 4. So this is a difference of a Lyman series. Here I'll show. This is equal to 13.6 by 4. This is for the Lyman series. Okay, let's calculate for the Balmer. Like for Balmer, it will be this. This is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. This is first line for the limit. Like Balmer, it will be this. The smallest energy gap will be this, right? Then it will keep on increasing. It will keep on increasing. And highest is from infinity. N is equal to infinity to this. So for Balmer series, nu bar max will be is equal to could be written as 13.6 into 1 minus 1 by infinity, right? So which will be is equal to 13.6. Sorry, this will be 1 by 4, no, because n2 is n1 is 2, right? So 1 by 4. So this will be is equal to this. And nu bar minimum for this will be 13.6 into 1 by 4 minus 1 by 9. This is the minimum line of the Balmer. So 1 by 9. So this will be is equal to 13.6 into 5 by 9. Sorry, not 5 by 9, 5 by 36. So delta nu bar for a Balmer. Again, oh, I think it's coming into the behind my window. I'll take it this over here. Balmer will be is equal to maximum, that is 13.6 by 4 minus 13 by 6 into 5 by 36. So what I can take common is 13.6, 1 by 4 minus 5 by 36. So this is 13.6, 13.6 into 31 by 36 into 4, right? So 1 minute, student. What mistake we made over here is 1 by 4 and 1 by 9. So this will be again infinity 1 by 4. Some calculation mistake is there. Then difference will be 13.6. We don't have to do so much. What I can do is this could be written this way, no? Why to do so much calculations? We can write this term as 1 by 4. This term as 1 by 4, right? So difference delta nu Balmer will be is equal to maximum is this, so it will be 13.6 by 9, right? So this is the answer which we will be getting 13 by 6 by 9 Balmer. So ratio of this nu bar Lyman by delta Newmar of the Balmer, that is what is asked. So this is how much it was for the Lyman? It was 13 by 13.6 by 4, and this is 13.6 by 9. This and this will get cancelled. What remains is 1 by 4 and 1 by 9. So this will be 9 is to 4, right? That will be a ratio of it. So the option over here is B is correct.